Hi, this is Professor Fernandez. We are going to work on class notes D in in lesson 12. So in this example, we are asked to show that the two vectors x1 and x2 are linearly independent. So, normally we do that by looking at the condition c1x1 plus c2x2 equals the zero vector and showing that all the c's are zero. That is the definition of linear independence. That will certainly work here. But this example's point is to illustrate this fact. So we have developed a lot of information, a lot of knowledge about the column space in this lesson and how it relates to solving AX equals B and Cramer's rule and all that sort of stuff. In this particular theorem, we've gotten one nice little side result, right? And the proof is down here, which is that if A is an n by n matrix, then the determinant of A is non-zero if and only if the columns of A are linearly independent. So that is a nice result. What does that mean in practice? That means that if you don't feel like calculating the determinant of a matrix and you just want to, for whatever reason, you want to make sure that the determinant of A is non-zero or zero, right? But you just don't want to calculate it. Then you can look at the columns of A. And if you show that they are linearly independent, that tells you the determinant is non-zero. If you show that they're linearly dependent, that tells you the determinant is zero. And vice versa. If you know the determinant is zero, then the columns are linearly dependent. Okay, so this is useful in many directions, all of the ones I just described. In this particular example, it's also useful because it helps us show that vectors are linearly independent by using the determinants. So we're going to say here to show that x1 and x2 are Li, the theorem we just talked about, 12.2.2, theorem 12.2.2, asks us to show that if I put these vectors into a matrix so that they become the columns of the matrix, then I want to show that this determinant is non-zero. Okay, and this is a 2 by 2 matrix, so the determinant here is what we did a long time ago in the course. We multiply the diagonals, 7 times 2, and then we subtract the product of the off diagonals, 4 times 3. All right, so what do I get? I get 14 minus 12, which is 2. And that certainly is not equal to 0. So that implies by theorem 12.2.2 that x1 and x2 are linearly independent. All right, so again, this is a simple enough set of vectors that we can, investigate linear independence through the definition of linear dependence that we've been using up to now. But it's nice that we have another condition now using the determinant to verify linear independence, and that comes in very handy if the vectors get much bigger. Vectors with 3 components, vectors with 4 or 5 components. Then we can use a lot of the properties of the determinant that we had talked about in that lesson. For example, taking the determinant of an upper triangular matrix or lower triangular matrix being the product of the entries down the diagonal, right? So we can leverage all of those properties of the determinant to then make our calculation of linear independence or showing linear dependence much easier.